In this section, we'll talk about the calculus involved with parametric equations. Now, when it comes to derivatives, there's really no difficulty in explaining to students exactly how that works, especially when it comes to the first derivative. Because the first derivative, we have the two functions, x equals f of t, so a parametric equation in the x direction, and a parametric equation in the y direction, g of t. And the derivative is just the derivative of the y direction divided by the derivative of the x direction. And there's not really much difficulty in explaining that to students. I'll show you a quick proof just so you see it, but I really want to explain what happens in the second derivative because it's a little bit surprising when you compare it to the first. So when I'm doing dy dx, so this would be the derivative of the slope of the curve overall. I can use the chain rule, and I can say that that is dy dt times dt dx. So chain rule just allows me to introduce a new variable into my differentiation process. And this notation, dt dx, looks a little bit strange, but I can work with this a little bit. I can say this is the same thing as dy dt over 1 over dt dx. All right, so I've effectively moved the term dt dx into the denominator, but in order to make sure everything still equals the same value, I had to put 1 over that. And then in order to continue, I can rewrite this having dy dt in the numerator, and 1 over dt dx I could rewrite, in fact, as dx dt. And so essentially, this is just the derivative of the function y and the derivative of the function x. So all I need to do is just take those individual derivatives separately, which is great. That's a very easy process generally to do, so long as the actual derivatives of those functions are easy to find. Now the second derivative, things get a little bit more confusing, because you would think that the second derivative you would end up just simply doing y double prime of t over x double prime of t. And many students do that, although it's not correct, unfortunately. So we can't do that. Here's what we have to do instead. We take the second derivative using this formula right here. So this formula tells me to take the second derivative of y with respect to the variable x twice, and that works out parametrically as d dt of dy dx over x prime of t. Let me walk you through a little proof so you can kind of get an idea of where this comes from, and that way you don't fall into this trap of trying to simply do the second derivative of the function y over the second derivative of the function x, because that doesn't work. It will not give you the correct answers except for possibly some coincidental values. So let's take a look at what this would mean. The second derivative of y, of the function y, with respect to x twice. So this would be d dx, so the derivative with respect to x, of the first derivative. Okay, that should make sense. That's how we do a second derivative. We take the derivative with respect to the same variable of the first derivative. That's the second derivative. Now the first derivative we saw is the same thing as dy dt over dx dt. So I'm taking the derivative with respect to x of this thing. And this is kind of where the trouble comes in, because we have to use the chain rule again, just like we did with the first derivative. But what that looks like is d dt, so I introduce the new variable t of this function, the first derivative, times dt dx. Now that is the same step that we did in the previous. It's just we only had the function y in this position with the first derivative. Now we have the function that represents the first derivative. So we have to be careful. And what that works out to is this. Using the same reasoning from the first derivative, I can basically take this term dt dx, put it in the denominator by putting 1 over that value, and then putting it into the denominator. So I'll do the same thing. It will invert it. So I essentially get d dt of dy dt dx dt over dx dt, which essentially tells me that what I have to do to get the second derivative is to take the derivative with respect to t of the first derivative and divide that by the derivative of the x component. Third derivatives, fourth derivatives, any further derivatives will follow the exact same pattern, but you definitely want to watch out for and not get caught into the trap of thinking you just need to do the second derivative of the numerator function and the second derivative of the denominator function twice. Okay. So let's look at an example. Find the slope and concavity of x of t equals square root of t, y of t equals 1/4 t squared minus 4, for t greater than or equal to 0 at the point 2, 3. Then find the equation of the tangent line at that point. So we're doing all the different things that we did with derivatives from Calc 1. We're just doing it in parametric equations, that's all. So if I want slope, I would resort to looking to the first derivative, dy dx. And if I want concavity, I would look to the second derivative, just like we laid forth in Calc 1. Again, we're just doing this in terms of parametric equations instead of standard functions. All right, so let's use the formulas that we developed and establish what the first derivative is to begin with. That's an easy starting point, because if I have knowledge of my functions, x of t and y of t, then I know that dy dx is just simply y prime of t over x prime of t. So in this case, y prime of t, I would have, well, tell you what, let me rewrite that a second. So let's change this into 1/4 t squared minus 1. All right, and that'll just make it a little easier to differentiate. So differentiating that, I'd bring the 2 down, so that would be 1/2 t. And then the derivative of a constant is 0, so 1/2 t would be that answer. And the denominator, x of t, I could rewrite this as t to the 1/2 power. So bring the 1/2 down, so 1/2 t to the negative 1/2 by subtracting 1 from the exponent. And of course, simplify. It looks like the 1/2s will cancel, which is nice. And I would have t to the 1 minus negative 1/2, which would be t to the 3/2. And that would give me the first derivative. Now, if I want to find the slope, what I need to do then is I need to evaluate the first derivative at the point given. But the thing is, this is a function of t, not of x and y. So I can't just plug in 2, which is normally what I would do for a derivative and finding a slope. I have to figure out what value of t results in the 0.23. So you can do this in 2 different ways. So every single point, let me pair off some space here. Every single point has the coordinates x and y. All right, x and y are defined by the functions square root of t and 1/4 t squared minus 4. Right, so there's some value of t that resulted in each of these functions to be equal to 2 and 3 respectively. So I could set, say for instance, the x components equal to one another. Whoops, that was the y, sorry. And say square root of t equals 2. And that would tell me that t is equal to 4. All right, so that was using the x. Using the y, I could say the y component set equal to 3. Well, let's see, that would be t squared minus 4 equals 12. And if I add 4 to both sides, that would be t squared equals 16. So t would be positive or negative 4 in that particular case. But we've got t equals 4 for the x. So that matches up at 4. Either way, you get the same result. Now, the value of t is what we need to plug into the derivative in order to come up with the slope. So this would be 4 to the 3/2 power. And the denominator of 2 is a root. So that would be the square root of 4, which is 2. And then we take 2 to the 3rd power, which gives me 8. So the slope at this particular point is 8. Okay, let's now turn our attention to the second derivative. So the second derivative is a little bit different in order to calculate it. So d squared y dx squared, we are told is the derivative with respect to t of the first derivative, which is t to the 3/2 power, divided by x prime of t, which is 1/2 t to the negative 1/2. Same x prime as in the first derivative. So if I take the derivative of t to the 3/2, that's going to be 3/2 t to the 1/2 power all over 1/2 t to the negative 1/2 power. 3/2 won't cancel with 1/2, but it will reduce to 3, so that's nice. And then t to the 1/2 over t to the negative 1/2, we would do t to the 1/2 minus negative 1/2, so that would be t to the first, so 3t. And we then find our concavity by plugging in to the second derivative the same value of t. All right, so when I plug in t equals 4, that's going to be 3 times 4, which is 12. And the value of the concavity isn't always as important as just simply, it's telling me that it's concave up or concave down. So in this particular position, we are concave up. Now the last thing requested in this example was to find the tangent line at this particular point. And the tangent line, we still come up with in the exact same way in Calc 1. So we use our point slope form of a line, and we take all the known values and just plug them in. So this is really just reiterating that we can do the exact same stuff with derivatives of parametric equations that we could with regular functions. So the y value of the point in question is 3. The slope was 8, and the x value was 2. And if we simplify this, we would have y equals 8x minus 16 plus 3, or y equals 8x minus 13. And just to show you that this does work out the way that we expect it to, let's take a look at everything on a graph. So I'll bring up the calculator here, and let's change first into parametric mode. And let me make that larger. All right, so I can now draw the graph of my parametric equations. I've got some things to clear out here. I'll turn off this statistics plot. All right, so my parametric equations were the square root of t and 1/4, so I'll just do 0.25 times t squared minus 4. Okay, and we were looking at the point 2, 3, and we came up with a tangent line. So the tangent line is a rectangular equation. I would need to parameterize it. Easy way to parameterize it is just let x be t, and then y would be 8 times your x variable, which is t, minus 13. So that's a fine way of parameterizing a rectangular equation. All right, so let me check my window settings. That looks fine. There was no parameters given for, oh, you know what? It did say t greater than 0. Okay, so let's start with t equals 0. And that's actually another thing. You'll notice I came up with positive or negative 4 here. If t has to be greater than 0, then that sort of reinforces that t would be, t equals 4 would be the correct value there. All right, let's graph, see what happens. Okay, so here's my graph in blue, so that's the curve, and then the tangent line is in red, and you can see the point 2, 3, which is about right there, so we're centered up right on that particular point. So everything works out fine.